Good evening, everyone. This is SMC from the year 2000. Question number 25. Another brutal geometry question here, but very fun actually to get. I was very happy when I got this. So let's get straight into this. So the figure on the right shows two parallel lines, L1 and L2. Line L1 is tangent to the circles C1 and C3. Okay, so it just touches C1 and circle C1 and C3, as you can see in the diagram, right? So at this point here, right, as well as at this point here, it's just going to touch circles C1 and C3. And similarly, line L2 is a tangent to circles C2 and C3, right? So you can see that line L2 effectively just about touches circle C2 at some point over here. And it just about touches circle C3 at this point here, okay? Right, okay. And the three circles touch as shown. Okay, so yeah, so C1 touches C3 at this point, and C3 touches C2 at this point, and then obviously C2 touches C1 at this point. Okay, so you have those are all your points of intersection, and they're really the points that you kind of like, because it means that when you sort of draw line segments through those points, you can basically not add any additional lengths that you don't know about, right? Because for example, if I were to have let's label my centers of my circles first of all. That's always important. So if that's O1, O2, and O3, so those are just the centers of my three circles. Suppose I was trying to find, let's say, this length, right? Some arbitrary length like this. Well, I have this length out here, right? Part of that length is just the radius r that we want to find. Okay, but the other part of that length is like, what the hell is this, right? Like, it's just you're never going to be able to find that, right? Or it's going to be disgusting to find it. So that's why we prefer to deal with the points of intersection, because then we'll be able to know that we're not adding in any extra length that we can't account for. So for example, this length here I know is just r. Like, there's nothing else going on, and this length here is simply going to be r plus t, right? Because I'm not adding in. There's no, like, at this point here, it's literally where the two circles touch. So there's no point at which this line will go outside of the effectively circles, right? It's always going to be within them. So I can account for all the distance without like adding in any extra distance. Yeah, effectively that would be there if there was like a gap between the two circles. Okay. Right. So, okay, so we have our three centers. Did I even finish reading the question? Okay. Circles C1 and C2 have radius S and T respectively. What is the radius of circle C3? Okay. So obviously, though, we want that radius in terms of the other radii. So we want the radius of circle C3 in terms of the radii of circle C1 and C2, S and T respectively. Okay, and obviously there is this option here, which they kind of put in the. I noticed that UKMT put this option in a few of their older SMC papers. More information needed. I'm not sure if it ever was that. Okay, I actually think I fell for it once when I was doing a question with my friends, and they quickly corrected me. So I really highly doubt. I think this is sort of more of a throwaway option than like a serious consideration option. I'm not sure if it ever has been this though. If it has been this, then I guess you need to take it seriously. But I think it's kind of a stupid option to put in there because it's also hard to verify. How am I supposed to know for sure that there's more information needed? Whereas, for example, if I were to do the geometry and get this answer, for example, then I would know for sure that this is the correct answer. But you can never really know for sure that more information is the correct answer. So it just feels like a stupid thing that they put there. So that's probably why I don't think they put it in any recent papers. But it was an option back in these days, and I think it's safe to say that you could ignore this option. I'm not sure if it ever was this option, but that just makes it even worse if it never was this option, because then it's just basically an even easier question, because now you have less options really, so a higher probability of just guessing it correctly, right? But whatever, right? That's out of the question. Basically, we'll be ignoring this option. More information needed. I might talk about why you might think it is this option, but really, I think it's safe to say that we just leave it out of the question. Okay, so what's the radius of circle C3, right? So there is actually a way to do this, which I realized after solving it, that effectively just, because I remembered that this is the way I did it with some other friends previously, which actually just doesn't even involve a geometry, like a geometry bash. You could just do this by basically considering different numerical values of S and T. So specifically, you might want to consider the case where S is equal to T. And so maybe in that case, what you're going to get is something like this, right? You're going to get two circles which are like about the same, like are going to be exactly the same sort of size, and then resting on top of a circle C3, which looks something like that, right? And so maybe you can do some sort of geometry with this configuration, right? And the case where S is equal to T, to basically find what the result will be there. It's probably easier to work with in that case. And then you can see, okay, the result that I get from that, right, does it not translate to any of the four options up here? And if it doesn't, then I can cross those options off because it doesn't work all the time. Okay, and so that's one way of doing it. But then I think you do have to do a little bit more to actually discern which option is correct, right? Because obviously when S is equal to T, then what I get for B is 2S, and what I get for C is also 2S, right? So effectively, those two options are the same in that case. So I'm going to need to do a little bit more to discern between those two options, right? But effectively, yeah, you can do that, right? I'm not entirely sure how the argument for that works, but I know that it probably would get you somewhere. You make some progress, and it probably involves a little bit less geometry on the whole than the solution that I'm about to show you. So if you want to do that, then that's perfectly fine. However, if you want to just geometry bash like me, then you can notice the following. So the first thing that you're probably going to notice here is the following triangle. So O1, O3, which is a straight line, by the way, right? Because they both pass through this point. Okay, and effectively at this point, if I were to draw a tangent line, then the angles here and here would both be 90 degrees. Okay, so effectively what we can say is that the gradient, so if I were to label this point, let's just call it M or something, whatever, maybe just capital M, right? Then effectively O1M is effectively going to have the same angle with my tangent as O3 as effectively the line O3M. Okay, and so they're effectively the same inclination to the tangent, which means that effectively they have the same gradient and they're just one straight line, right? Because if this wasn't 90 degrees, right, and by the way, these are 90 degrees due to the circle theorem, right, which says that effectively, like the chord from the effectively center of the circle to the circumference is going to be perpendicular to the tangent line. So effectively, if it was like any sort of, if it was sort of not 90 degrees, if it was like some pointing over here, some other non-trivial angle that wasn't 90 degrees, right, then it wouldn't be a straight line, right? It'd be two like sort of lines, two straight lines, which you have to consider separately. But we don't need to do that here because they actually both make the same angle with the tangent, and so they're both effectively the same line. So O1, O3 is just one straight line, okay? Which I was a little bit like unsure whether to accept that at first, but then that was kind of the way that I reasoned through it. I think that's an okay argument. Yeah, like I want to say that's okay. Yeah, because there'll only be one line, right, that's perpendicular to that and passes through that point in 2D. So, and so yeah, so they're forced to basically be the same straight line. You could probably make that more rigorous, but that's not really the point of the question anyway. I just wanted to make it known. And then we also have O2, O3, which by the same reasoning is a straight line, and O1, O2, okay? And we know each of the lengths, the side lengths of this triangle, okay? We know them because, as I said, we're not losing any information. Did I say that in this one, actually? Maybe that was a previous attempt at this. Effectively, we know that we're not losing any information in terms of distance by choosing, for example, this distance O3, O2, right? Because we know, for example, that if this radius is R, then effectively this distance here is just going to be R plus T, right? Because T is the radius of C2. Okay, so I know exactly what that distance is going to be. Whereas let's say that I chose a distance like O3 to this point over here, then effectively, I mean, I would know that, but let's say I chose it to this point over here, then how the hell am I ever going to find this out, right? Like, it's pretty much impossible to find that. Well, I mean, there might be a way, but it's just like, you would prefer things that are a little bit neater, and probably SMC will also have solutions which are neater in style. They're not going to involve too many extravagant constructions. I mean, the constructions are still require some thought, but I highly, if there is an easy length for you to calculate, an easy length, an easy sort of construction for you to work with, or an easier construction for you to work with, then that's probably going to be the one that they want to use in a sense. Or in any case, I think it's best to try things out with that first. Because it just feels like there's more options there, right? There's more options here because I have side lengths. I have information about this triangle, as I don't really have any information, or it doesn't immediately jump out to me how I get like this length, for example. So yeah, so we start by looking at this triangle, okay? So obviously we know the side lengths of that triangle. I'm going to draw it down here as well. So we have a triangle that looks something like this. The side lengths are R plus T, R plus S, okay, and S plus R. No, sorry, S plus T, right? And R plus S, right? So at this point, you might try and think, what about cosine rule or something, okay? And when you do cosine rule, you get a very long expression, okay? Which I think I did before, actually, if I could find it. Yeah. You get sort of this kind of expression, right? I mean, it's not going to be exactly this, but effectively... Oh, sorry, I really was... Yeah, effectively, you get something kind of mad like this. And like I tried factorizing it and doing some stuff with it, but obviously you just have this cosine alpha term in there. You're never going to be able to do anything with this because you don't know what alpha is. Okay, so I spent a very good portion of time. I spent about an hour doing this, by the way. I spent a very good portion of time thinking to myself, like, what am I going to do if I have that cosine alpha? Which makes you think, oh yeah, more information needed. I need alpha, right? I need alpha to figure it out. But actually you don't, right? It's just another way around. There's a way to avoid it, effectively. Because it was very quick to my attention that, like, they haven't really given me any information about angles. The only angle that they've given me is the 90 degrees at the tangency points. But, like, how am I going to, like, there's no way I can deduce anything else from that. So I think I'm going to need to wait. There's got to be a way around this without angles. Unless it's more information needed. But again, it's like, how can you tell? I feel that option is more silly than, like, actually serious, though. So I don't know. So I kind of dismissed it. But ultimately, this triangle by itself is just not enough. Okay, but it's a good start, and I think you should keep it here for now. Another thing that we know, right? Another length that we do know is this one. Okay, so we are going to know, obviously this here, right? This length here is just going to be 2r, right? Effectively. Okay, because obviously this point is a tangency point. To the center, that's going to be r. And then the center to there, that's also going to be r. And now that's coming to my attention, do we know that it's vertically horizontal? I mean, I think we do know that it's vertically horizontal because those two lines are parallel. Yeah, exactly. So we know that it's going to be vertically horizontal because L1 and L2 are vertically parallel. Okay, and because they're tangent, so this will be 90 degrees. This here will also be 90 degrees. So the same angle is made of those two lines. And so effectively, you're going to get the exact same line because they both the lines have to pass through the center. So the line that's perpendicular to effectively the line with the same gradient, effectively, even though it's infinity, effectively will just be a horizontal line. So a line perpendicular to a vertical line will just be a horizontal line. And it's forced to pass through the center of C3, which is O3. So therefore, effectively, it has to be one horizontal line, which is effectively of length 2r. But again, those semantics there are not important. The most important thing is just that length 2r, okay? And of that length 2r, we also notice the following information. Obviously, O1 here, this length here, so O1 to sort of the point of intersection with L1, that's just the radius of C1, so that's S, right? And similarly, this length here, from C2 to the point of intersection with L2, right? That's going to be a horizontal line as well, because of course 90 degrees here, and that's going to be of length T, okay? And so so effectively what we have, therefore, is we have effectively this length here, right? Already I could draw it as this length here. This length here, up to this point, is going to be of length 2r minus s minus t. Okay? So that length there is going to be what, 2r minus s plus t, effectively, minus s minus t, right? So there's a lot going on with this geometrically here, right? But effectively, because we have that horizontal length 2r, we have t, we have s, so that there is going to be 2r minus s minus t, right? Because if we just like project that horizontal line down, then we can just fit that length t here, right? And so we know what that length is, okay? Right, I guess it's still kind of unclear though, like what am I really doing? What's going on here? What am I getting to? And I guess, yeah, it's a good question. But one triangle, I think the first triangle that stood out to me was this one. Okay, so we have this triangle down here. So obviously we can just project, so this length x, s, we can basically just project a sort of vertical line down from this center of C1, so O1. That basically lands on this line here that passes through the center, this horizontal line passing through O3, which is effectively going to be a length that we don't know as of right now. But we are going to be able to figure out this, and we know this, we know the hypotenuse of that, and effectively because it's a horizontal line, that's a vertical line, that'll be 90 degrees. But we do know that obviously the hypotenuse, we already have that, because this is r plus s, right? So that's going to be r plus s. Now we need to just figure out this length, okay? So the length, that's not sort of the, so let me just highlight it. So effectively we need to figure out this length here, right? And the way that we can do that is by effectively realizing the following. So effectively what do we do? So if we were to sort of go down from here, per se, let's just go straight down like this, right? So imagine that's a straight line, so then you get a 90-degree angle. Okay. Well, actually, yeah, I mean, you can also do that. But effectively, the main argument is that obviously from the center of C3, so from O3 to this point of tangent C here, that is the radius of C3, so that's of length r. And we know that this length is just s, right? So then this length has to be r minus s, effectively, right? So that's length r minus s. And the reason for that is just because effectively, this length here, as I was saying, this length here, that is length r, right? And we already know that this length here is length s, so we can just project it down like this, so that's going to be length s as well. Okay, and so actually we can calculate that this length here is r minus s, and this here is r plus s. So we can calculate via Pythagoras' theorem that length there, that length, that vertical line. So length of vertical line, right? So the length of vertical line is simply just equal to, right, r plus s all squared minus r minus s all squared. So it's going to be r squared add 2rs add s squared minus in brackets r squared minus 2rs add s squared. So these are going to cancel, and you're just going to get 4rs. So that's obviously going to be the length squared. So you square root it, right? So you can get the square root of all of that, the square root of all of that, which gives you the 2 times the square root of rs. So that's the length of that vertical line here, 2 square root rs, okay? So now that we've done that, we can use the same argument with this sort of vertical bit here, right? So effectively, this is also a vertical line. So with this vertical line here, right, that we can make, we can use the same sort of idea, right? It's literally the exact same, except it's going to be r minus t and so on and so forth. So this vertical length here is going to be 2 square root rt, right? Which is just the length in black like that, from just the right angle triangle geometry again. Okay, and so at that point we have a lot of information, right? And I'm gonna rub out some information that we don't really need anymore. Okay, so we don't really need that. We'll keep it O3. You can take this out. You can take this out. Doesn't not necessary anymore. Okay, so we have that. Yeah, okay, fine. So that's probably going to be okay. Let me also just take this out. Right. So now, what's going to be important is we need to look at this final sort of triangle over here. So this triangle here, right? Effectively, that's going to be important to us, okay? And what we want to find is this vertical height here. Because if we have that vertical height here, right, then what we can do is we can say that this vertical height, this, plus 2 square root rs is equal to 2 square root rt, because those are just vertical lines, right? So those lengths are just the same. But effectively, 2 square root rs is a little bit shorter than 2 square root rt, just from looking at it, right? So we can, if we find out that length, then we can just say that, right? So we can set up an equation and solve it, right? So we need to find out that length first, though. Now, obviously, we already have that effectively. So this horizontal length here is effectively just going to be just 2r minus s minus t, right? So that's what we have up here already, because obviously this length here that's t, this length here that's s, and so the whole length is 2r, right? So you can just do 2r minus s minus t, or 2r minus in brackets s plus t for that length. Okay, and the hypotenuse is already known. It's just the sum of the radii, right? So it's just going to be s plus t, right? So that's going to be the hypotenuse. So then we use Pythagoras on that, okay, to get the length of the vertical line 2, effectively. So 1. Actually, and then we have obviously from before that the length of vertical line 2 is equal to obviously 2 square root rt. So that's just the same argument as above. Same argument. Right, and then the next bit that we need to calculate now is the other bit. So length of vertical line 3 is equal to, so via Pythagoras, it's just going to be equal to the square root, right, of s plus t all squared minus, so then 2r minus in brackets s plus t all squared. So just looking at it separately, we can do some algebra to figure out that 2r minus in brackets s plus t all squared. And I kept messing this up, by the way. I messed this up so many times. So let me just make sure that I do this correctly. So this thing here, that's equal to 4r squared, right? Minus 4r multiplied by s plus t, right? And then add s plus t all squared, okay? So then this thing inside the square root is just going to be the square root of s plus t all squared, right? And then it's going to be minus 4r squared, add 4r times s plus t, and then minus s plus t all squared. So you don't even need to expand those brackets, right? So if you can avoid expanding brackets, then good, because it's just a lot of it's just extra work, right? So we can cancel those things out. So that cancels out very nicely. And this just gives us effectively the square root of 4r multiplied by s plus t minus 4r squared, which is effectively the same thing as 4, the square root of 4 multiplied by r times s plus t minus r squared. So the square root of 4 is just 2. So that's just the same thing as 2 the square root r times s plus t minus r squared. So I know this looks bad, okay, but this is the length that we care about at the moment, okay? And trust me, just believe me, it will work out, okay? And I'm pretty lucky this worked out. This is quite a hefty bunch of things you have to do for an FMC question, in my opinion. But whatever. So then you get that, and effectively that is the length of the vertical line, right? This blue bit up here. And so once now you have that, so you can say that plus 2 square root rs is 2 square root rt, okay? So this is just a final equation, right? So final equation is effectively as follows. So 2 square root r times s plus t minus r squared is equal to 2 square root, what was it, rs? No, I need to be careful actually, that matters. It's 2 square root rt minus 2 square root rs, okay? Minus 2 square root rt minus 2 square root rs, okay? And then we divide both sides by 2. So you just now get that the square root of r times s plus t minus r squared is equal to the square root of rt minus the square root of rs. Now square both sides, okay, and what you're going to get? You're going to get r times s plus t minus r squared is equal to rt minus rs, right? And then it's going to be minus 2 times the square root of r squared st. So there's going to be 2r, effectively, because r is positive, right? 2r times the square root of st, right? Okay, so there we go. And then when we expand the left-hand side, it's going to give us rs plus rt minus r squared is equal to rt minus rs minus 2r square root st. Okay, so effectively... No, sorry, that should be plus rs, shouldn't it? Because this is minus square root, so when you square both sides, it's going to be a plus rs, right? So that turns into a plus. This will still be a minus, though, because it's minus square root r squared st minus square root r squared st, right? So effectively, this stuff all cancels out, right? So all that you have is, and then this obviously implies that minus r squared is equal to minus 2r square root st. Obviously, r is not going to be 0, otherwise there is no circle C3. So you can divide by r. That gives you minus r is equal to minus 2 square root st. Okay? And so, to finish off, you get that r is equal to 2 square root st, right? Which is hopefully one of the answers. Yes, it is option number C, letter C. Okay? Which is the correct answer to the question. What a ridiculous question, though. That is actually probably one of the hardest SMC questions ever. There was a harder, probably repugnant one, like with the fucking 1, 1, 1, 1, 1, and then you had to do like some process of squaring the number and then adding, like scaling it up and so on and so forth to get another like repugnant or whatever you call it, like with the 1, 1, 1, 1, 1. That was really difficult. This is also quite difficult, but I think this was still doable. Maybe the other one was doable as well if I had enough time. But yeah, this took me about an hour to solve, so very tricky problem. Definitely would not get it in the exam, but nonetheless a very fun problem to solve. Okay, awesome stuff.